So, monolith versus microservices. At high level, a monolith is one application that we deploy as one unit. All the code ships together. Microservices means we have taken that same application and split it into several smaller applications, and each one ships on its own. That is the most useful practical difference. One deployable unit or many. And notice the word I keep using deploy, not size, because the word micro makes people think it is about how many lines of code are in that thing, right? It is not. A microservice can be a quite large one. What makes it a microservice is that we can build it, test it, and release it on its own without touching anything else. So, the real question in this whole debate is when I want to change one thing, how much of the system do I have to ship? And think about a food court. One option is a single big kitchen, one menu, one team, everything cooked in the same place. And the other option is five different stalls, each one with its own kitchen and its own shutter. Now, what actually separates the two? If one stall shuts for cleaning, the other four keep serving. But if the single kitchen shuts, everybody goes home. And that is independent deployment. And hold on to this, the stalls are only really independent if one customer's meal does not need every stall to respond. So let us be fair to the monolith first, because I think it has got a bad reputation that it mostly does not deserve. A monolith is not a big ball of mud. It is not old code. It just means the parts live together and ship together. So, for example, inside our shops application, we would still have clear areas orders, payments, email, search. The modules might even sit in different packages or repositories. What makes it a monolith is that they become one running application and get released together. And in our simplified picture, they are all running inside the same program as well. In production, we would run many copies of that whole application behind a load balancer. But we still build it, deploy it, and scale it as one whole thing. That is what makes it a monolith, not that it is one server. And that gives us two things that are genuinely hard to get any other way. One, when the orders part needs something from the payments part, it is a function call. There is no network round trip, nothing to serialize, that is, nothing to convert into a form that can travel over a network, and no remote service that can time out after it already received the request. The code can still fail, of course. It just cannot fail because the network between the modules disappeared. And two, for a request inside one instance, the whole call path is usually visible in one place, one stack trace. So, at high level, this is the same default. And this is not just my opinion. And Martin Fowler puts it about as bluntly as you can. He says the majority of the software systems should be built as a single monolithic application. And he says do not even consider microservices unless we have a system that is too complex to manage as a monolith. And he points out that Facebook and Etsy were shipping updates many times a day on monoliths as well. So, monoliths cannot ship fast was never really true either. So, if the monolith is fine, why does anybody ever leave it? And the honest answer is usually not because of the mission, it is because of the team. Three engineers in one kitchen is comfortable. 60 chefs in that same kitchen is a different thing altogether. And the first pain is releasing. Everything ships together, so everything has to be ready together. Even when my email is completely ready, it goes out into the same release artifact as payments and orders and search. So it shares their testing and their risk. And if a release breaks, we roll back the whole thing, including the 9 other changes in that release that were perfectly fine. So as the team grows, the release becomes a queue, and that queue becomes the slowest part of the day. Second, the failure lands everywhere. Search has a memory leak, and every module is inside that same program, so it crashes that whole instance. The other copies may keep the system up, but inside each copy, orders and payments and search all share one failure boundary, and they share one release as well. The same build eventually reaches every copy, so one bad release can affect every module, even when the change belonged to only one of them. And the third one is scaling. Let us say our search feature is doing 10 times the work of everything else. We cannot give search more machines by itself because search is not a separate thing we can run. So we scale the whole application. Every copy carries orders and payments and emails as well, just to get more search. And think about it, that is wasteful. But notice it is a money problem, not the system cannot work problem. And that distinction is going to matter later. Okay, so now let us break the kitchen up into stalls. Each area becomes its own application with its own deployment. Orders is one service, payments is another, search is another, and the code can live in separate repositories or all in one repository. That part does not matter. The deployable boundary is what matters, and they talk to each other over the network. Releasing. My email service ships when I am ready, and nobody else is in that queue. Failure. If search crashes, orders can keep taking money as long as orders does not sit there synchronously waiting on search. And we designed that boundary properly. It is not automatic. And scaling. Search is its own thing now. So search gets 10 machines and email gets 1. We pay for exactly what each part needs. And there is a fourth one as well, which is really the actual reason most companies do it. Each service can be owned by one team. That team picks its own release schedule. And the big one is the data. Each service owns its data. That might be a separate table or a separate database on shared infrastructure. The rule is that nobody else reads or writes it directly. So if order needs something from payments, it asks the payment service. It does not go poking around inside the payments table itself. So let us say a company has 200 engineers. It stops being 200 people negotiating over one code base and becomes 20 teams that mostly do not need to talk to each other. And the thing is, this is where most explanations go wrong. What microservices primarily buy us is independence, in ownership, in deployment, and yes, in scaling one part on its own. What they do not buy us is a faster request. Splitting things up usually makes the individual request slower because now there is a network in the middle. Right. So what does it cost? And the first one is sitting on every diagram and people look straight past it. The arrows. Think about it. We draw them as thin little lines and they are expensive part. In the monolith, orders calling payments was a function call. No network round trip, nothing to serialize, and it cannot half fail. Now it is a network call, so it can time out. And here is the horrible version of that. It can time out after the other service already did that work, and then our retry does the whole thing a second time. And think about one consumer request. In the food court version, that request walks to four stalls one after another. Every hop adds a little time, and every hop is a place it can fail. So, at high level, one cheap local call has become several remote calls. Every hop adds serializing, queuing, and network time, and every hop is another place the request can fail. And that is the trade. We bought independence and we paid for it in latency. And there is a nastier version of that. What if three of the four stalls succeed and the fourth one fails? In the monolith, if all of that state lived in one database, it could often be one transaction, meaning a set of changes that either all succeed together or all get rolled back. Now, payments and orders own separate stores, so one local transaction cannot cover the whole flow. We have taken the payment and we have not created the order, and there is no simple rule to undo that. We have to build the undo ourselves in application code for every flow that spans services. And then there is everything that is not the code at all. Every service needs its own deploy pipeline, the automated steps that build it, test it, and release it, and its own alerts, and somebody who gets woken up at 3 in the morning for it. And when something is slow, which service is slow, becomes a genuine investigation because the request touched four of them. In the monolith, that was one stack trace. Now, we have to run something that follows a single request across all four and stitches the whole path back together. And that is what distributed tracing is. And all of that is real work that no customer ever sees. So now the failure mode. And this is the one I most want you to walk away knowing because it is what actually happens to teams. It is called a distributed monolith. And at high level, it means we split the application into services, we deploy them separately, but they are still so tangled together that we cannot actually change one without the others. And there are three tells. The first one, to release a feature, we have to deploy three services in a particular order. That is not independent deployment, right? That is a monolith release with extra steps. The second, all the services are still reading and writing one shared database. So somebody renames one column in a shared table and four other teams' code stops working on the same day. And now those teams have to coordinate, which is exactly the thing we split up to avoid. And the third thing is the sneaky one. Every request has to go through all of them synchronously, and each one waits on the next. So, if any single service is down, the whole thing fails. Think about our food court. 5 stalls, and every single meal needs all 5 of them to respond before the customer gets anything. The kitchens are independent, and it does not matter at all because one closed stall means nobody eats. And look at what we are holding. We are paying the full price of being distributed. The network hops, the latency, the tracing, the pipelines, the on call for every service as well. And we are receiving basically none of the independence we bought it for. So we took on the cost of both and we got the benefit of neither. That is the whole problem. And this is not some rare mistake. It is a common way microservices migrations go wrong. We split a system for the wrong reason, and that is what we end up holding. So, a real one, Segment. They are a data company. They take your events and forward them onto other tools. And each place they forward to, they call a destination. And in the beginning, everything went through one shared queue. So, if one destination went slow, the retries flooded that queue, and every other destination got delayed behind it. One slow partner, and everybody waits. So they split it up. Every destination got its own service and its own queue, and it worked. That is the important part. Now, if one destination has a bad day, its own queue backs up, and nobody else even notices. So, this is a real case of microservices doing exactly the thing they are supposed to do. The isolation was not fake, they genuinely bought it. And then the bill came. They kept adding destinations, about 3 a month, and each one was a new service. So they ended up with over 140 of them. And more services meant more repositories, more queues, more deployment work, more scaling configuration, more operational surface for the same small team. And each copy of the shared libraries drifting off onto its own version as well. Their own write up says the overhead went up in a straight line with every destination they added. And by the end, they had 3 full time engineers spending most of their time just keeping the system alive. So they merged it all back into one service. And here is the part I want to be fair about. Because they were honest, and a lot of retellings or not. They say plainly what they gave up. Fault isolation got harder. One bad destination can now crash the service for everybody. And caching got worse. And the reason is interesting. The merged service runs across 3000 plus worker processes. So each destination's cached data is now spread thinly across all of them, and it is much less likely to be warm when the destination needs it. And updating one dependency can break several destinations at once. So it was not a free win. It was a trade they decided was worth making. And notice what the lesson actually is here. Splitting worked. It just cost more to own than it was worth. That is the whole thing. So that was a team splitting up and it working and still costing too much to own. And now the opposite problem. A real result that everybody read far too broadly. Amazon moved from microservices back to a monolith and saved 90%. The number is real, but almost everything people build on top of it is wrong. So let us go and read what they actually wrote. First, the scope. This was not Amazon. It was not even Prime Video as a whole. It was one internal tool owned by one team inside Prime Video, a team that inspects audio and video quality on streams. Is the picture right? Is the audio right? And each of those checks they call a detector. And in their own words, they never intended nor designed it to run at high scale. So that is a tool that outgrew its design. It is not a company changing its mind about architecture. And to be fair, the word microservices is theirs. Their own write up is titled A Move from Distributed Microservices to a Monolith. So the label is not the mistake, the scope is. And second, the costs. And there are two things here, so let us take them one at a time. The first, and this is straight out of their own write up, they ran the work using a thing called AWS step functions. At high level, it runs your job as a series of steps and it charges you every time the work moves from one step to the next. And for every second of a video, they were pulling out frames and running each check as its own step. So think about that. A lot of steps every second for every stream, and every one of them is built. And the second thing, when one component had to hand a video frame to the next one, it did not hand it over directly. It wrote the frame out to S3, which is Amazon's file storage, and the next component read it back in. And at that volume, every frame, every second, every stream, those storage calls got expensive. And again, that is them saying it, not me guessing. So it is not microservices are expensive, right? It is that moving data between components is expensive and paying per step is expensive. And here is the bit that gets left out completely. It was not only a bill, They say the way they used those components made them hit a hard scaling limit at around 5% of the load they were expecting. So, about a 20th of what they actually needed. That architecture could not reach the load they needed without being redesigned. And the fix was to put all the components into a single process. So, the data transfer happens in memory itself instead of going through S3. And that is where the 90% comes from. And they were honest about what they gave up as well. Before, each detector ran as its own service, so they could scale them one at a time independently. Now, the whole set runs inside one instance, so to get more, that instance has to get bigger, and that is exactly why they ran out of the room, which is where the ending comes from. And now, the ending, which I have basically never seen anybody quote. They kept adding checks and they ran out of room on one machine. So, what did they do? They made several copies of the service, and each copy got a different set of detectors. And they put a thin layer in front to send each request to the right copy. And their own conclusion is that it has to be decided case by case, workload by workload. And look at where they actually landed. Several copies, each doing a different part of the job, with a router in front. That is not one box monolith people draw in the comparison diagrams. It is a fleet of parameterized copies behind a router. And the useful thing there is the mechanism, not which label wins. So, how do we actually decide? And the first thing is to notice which question we are asking. Is our system big? Is the wrong one? How many people have to agree before we can ship? That is the right one. Because most of what we looked at today was that segment's problem was three engineers spending most of their time just keeping 140 services alive. And the monolith's problem is 60 engineers stuck in one release queue. Prime videos was the other kind. That one was about moving data between components. So, going by what these teams actually ran into, split when the pain is organizational, when teams are blocking each other to release, when one part genuinely needs to scale on its own, and scaling everything for it is costing real money, or when one part needs to be much more reliable than the rest. And there is no fixed number here, by the way. Fowler has seen 60 people running 20 services and 4 people running 200. So the headcount itself is not the signal, the coordination is. And do not split because the system feels big, or because a service sounds more professional than a module, or because we might need it in 2 years. And remember Fowler's filter, the button of proof is on splitting. We should be able to name the pain we are removing. And there is a middle option that lot of teams land on, and I feel it does not get talked about enough. It is called a modular monolith. And picture the walls going up inside that one kitchen, real boundaries, still one shutter. The idea is we keep one deployable unit, one thing to ship, one thing to debug, but we put real boundaries inside it, clear modules with rules about which module is allowed to reach into which. So we get the discipline of separation without paying for the network. And if one module later genuinely ends its own service, the boundary is already drawn. So pulling it out is a much smaller job as well. So the real question was never one box or 50. It is where do the boundaries go? And do those boundaries have to be network boundaries? And most of the time they do not. That is the whole thing. So let us put it back together at high level. A monolith is one deployable unit. Everything ships together. Calls between the parts are free. And one failure can take the lot down. Microservices means many deployable units. Each one can be shipped on its own and scaled on its own. And if we drew the boundaries properly, one of them failing does not have to take the rest with it. But every call between them is now a network call, and that can be slow or it can fail. And a distributed monolith is when we have done the splitting, but the pieces are still chained together. So we pay for distribution and we get none of it. And if you keep only three things, keep these. 1. The unit is the deploy, not the size. What makes something a microservice is that it can be released on its own. 2. What we are buying is independence, not speed. We can scale one part on its own, but the request itself usually gets slower because we put a network in the middle. That is the price. And 3. The boundaries matter more than the boxes. Neither of our two case studies landed on a clean answer. One split successfully and came back anyway. The other ended up as copies behind a router. That is the important part. So, if somebody asks you which one is better, I think the honest answer is that it is not really that kind of question. A monolith is the sensible place to start, and it stays sensible for much longer than people admit. And microservices are what we reach for when the organization, not the machine, has stopped being able to move. And if we cannot name the pain we are removing, then we are just paying the bill for nothing. See you in the next one.